Professor Juan de Dios. Can you hear me? Professor Juan de Dios? Yes, this time we may test the video, yes. So can you hear me? Alex?
Hello.
哎 ，Alex， 是你吗？你是不是
听到。
把这个教授的音频给关了？
不是，不是。
I am here.
Okay,
Can you
okay.
hear me?
Yeah.
Yeah.
Nice to meet you.
Okay, nice to meet you. Actually, good morning for you, Professor Juan de Dios,
Yes.
and good night for us. Yes.
Exactly.
Yeah, actually, I just checked Baidu, you know, and I found there are 12 hours about the time difference. But actually, we have 13 hours time difference. Yeah.
Right.
Yeah. And in the poster, I just told the others that the lecture will start 8:15. So we may have to wait 5 minutes. Yeah. So currently, I just found so far so good. We can see the see your slides. Yes, very clearly. Yes.
Okay.
And then before your presentation, I will give a brief introduction. Yes.
Okay.
Yeah.
I'm happy to wait. Don't worry.
Okay. And also, don't worry about us. Yes. We all sleep late. Yes. Yes.
Right. Yes. Okay.
So,
I will wait until you introduce me.
Okay. And currently we have 87 participants. Yes.
Yes, I saw it. It's a lot of people.
Yeah. Well, we may still wait. Sorry. So next time we may just talk face to face, you know, after COVID is to just disappear, you know. Yeah.
Hopefully.
Yeah, hopefully, yes.
Now we're also waiting for the elections in the United States.
Maybe half a day, yes.
Yes.
Yeah, maybe Biden.
Yeah, exactly.
Yeah. Trump is in danger.
Huh?
Trump is in danger.
Yes, I hope so. I hope he loses.
Oh yes, great. 88. Oh, still 87.
Hmm?
汤老师您在是吧？汤永利老师，对，我看您在这上面。
对，我在。
您一会儿记得提问啊。
好的。
好的。 Mhm. Dr. Mohammed, welcome. Kangkai, welcome. Professor Juan de Dios.
Yes.
Yeah, I think we can start. And before your presentation, I just give a brief introduction about you. Yes. So 晚上好，各位老师同学。Tonight, Professor Juan de Dios will give the presentation. The topic is discrete choice models in policy design. I just give a brief introduction about Professor Juan de Dios. He is the emeritus professor at Pontifical Catholic University of Chile. He received a doctor honoris causa in 2018 and the Life Achievement Award in 2012 and the Humboldt Research Award in 2010. He pioneered the application of discrete choice modeling techniques to determine the willing to pay for reducing externalities, such as accidents, noise, and pollution. He has published over 200 papers in archival journals and book chapters, and is co-author of Modeling Transport, a book published by Wiley, reflecting the state of practice in this discipline, which has sold over 17,000 copies and is now in its fourth edition. He is currently co-editor-in-chief of Transportation Research Part A and a member of the editorial board of several international journals. As I know, long time ago, there's one journal called Transportation Research. Maybe about more than 50 years ago, and this journal became two journals, Part A and Part B. And in recent several decades, then we have other journals like Transportation Research Part C, Part D, Part E, Part F. So this is a top journal in transport policy and practice. And discrete choice model is very popular in policy design. So let's welcome. So Professor Juan de Dios, maybe it's your time.
Okay, thank you very much, Sunny, and thank you all for being so late here to listen to me. I am very honored to have been invited to this talk in Jinan University, and I really hope that someday I will be able to go there and visit you personally. Okay, my talk today has, oops, this is not working. My talk today has the following parts. First, I will talk about the basics of discrete choice models. Then I will mention the kind of data that we use for estimating these models. I will mention briefly experimental design with some examples which are useful to let you know the kind of things that we can do with these type of models, which are very useful for then eventual policy design. I will then refer briefly to the state of practice in this area, which are the mixed logic and hybrid choice models. And finally, I will talk also about modeling with both a combination of revealed and stated preference data, which is again a state of the art and of practice. And I will provide you with a list of some publications that you may wish to have a look if you are interested in to see a little bit more, because this talk is obviously a brief account. Okay. Yeah. The basics about about discrete choice models. Random utility theory is the framework where we cast these models, and in its simplest version, we postulate that there is a type of person that we label kind of ironically Homo economicus, which is a person which is completely rational and has perfect information. But what happens is that there is the modeler, the analyst, who is an observer, and because the individual doesn't follow what the modeler can actually see and measure, it has to assume that the utility of a certain alternative, UIQ, a certain alternative I for a person Q, is composed of two elements, a systematic or deterministic utility, which we call VIQ, which is the part that the model can observe or measure. And because the rest he cannot observe or measure, he assumes that there is an error. And this error, epsilon IQ, is distributed with a certain density function. To generate, which is the simplest model and that has been used for many, many years, the multinomial logic model, MNL, these random errors, epsilon, have to be identically and independently distributed extreme value type 1, which has been called also Weibull or Gumbel distribution. And these errors have zero mean without any loss of generality. And they lead to a very well-known closed form expression, which is there in the screen, where the probability of choosing alternative I, individual Q, is the exponential of this deterministic component of the model divided by the summation over all the alternatives that are available to the individual. AQ is the set of alternatives available to the individual Q. And in this expression, there is a parameter, lambda, which is a scale factor and is actually can be shown to be inversely proportional to the unknown variance or standard deviation of the error function, and is actually unidentifiable. So we normally forget about it, but I will mention later, it is actually quite important when you're trying to mix data which has a different error nature, as I will be talking about revealed and stated preference data afterwards. Now, in many instances, it just is enough to consider linear in the parameters systematic or deterministic utility functions. And these functions have the form of a summation of parameters theta ki that multiply attributes x. And these attributes can be both level of service attributes, such as price, quality, or time and cost in the case of transportation. Or also we can have socioeconomic variables that reflect the individual that we are studying, like, for example, age, sex, income. And also the utility VIQ includes a n-1 alternative specific constant, ASC. And these constants take the value 1 for the option that they are appearing in. For example, if we have 3 alternatives, there will be a constant for the first and a constant for the second, but we have to take one of these alternatives as reference and assign to it a 0 as the constant. And this is a second identifiability issue, because we cannot have all alternatives with a constant. There has to be reference options, because the model, as you saw in the previous slide, would work on the basis of utility difference, because you can always divide the numerator by the denominator, and then you have differences of utility as the thing that matters in this particular model. The multinomial logic model, in the form I just put to you, cannot deal properly with correlation among alternatives, with heteroscedasticity among alternatives and individuals, and also it cannot handle variations in taste, because the parameters theta ki, as you can see in the equation, are fixed for the individual. They don't depend on the individual. However, even in those conditions, the model has been shown to be very robust to less than extreme violations in all these sense. For example, there might be mild correlation and the model performs well. There might be moderate heteroscedasticity and the model performs well. To treat this taste variation problem, which is actually very important, we have come to work with what we call systematic taste variations, which is interacting the utility, interacting the socioeconomic variables or other variables that have to do with the alternative with the level of service variables. For example, in that equation, I'm saying that the utility, for example, is a summation of parameters, of attributes x, k, I, q, which are multiplied now not by only one single parameter, but they are multiplied by a function which depends on a basic parameter, theta k, and then on a summation of parameters which are multiplied by the socioeconomic variables. For example, the parameter for x being time, for example, could be a basic value for time plus a list of parameters like age multiplied by age, by the age of the person, sex multiplied by the sex of the person, income multiplied by the income of the person, etc. And so you will have then that your parameters are no longer fixed for each individual, but they are actually variable and they will be equal only to individuals of exactly the same sex, age, and income, but different for others. So that is what we call systematic taste variations. And when we do that, we have a model which is a much better model, a much more flexible model than otherwise. Now, the multinomial logic model, and in general, all these discrete choice models are estimated using maximum likelihood, and there is an array of statistics that are available to test the goodness of fit. In the book that Sunny mentioned at the beginning, Modeling Transport, we have in chapters 7 and 8 a very complete description of all these statistics. The maximum likelihood estimates by its nature, the parameters which are estimated in that way distribute asymptotically normal and are unbiased. So we have that because the utility is a sum of parameters multiplied by attributes, the parameters can be taken as marginal utilities. So if we take the ratios of these marginal utilities to the ratios to the price variable, we can get what we call willingness to pay, WTP. And these willingness to pay estimates are essential in valuation studies, of which Sunny also mentioned that they have been pioneering the use of these willingness to pay evaluations for externalities in the case of transportation. An important extension to the multinomial logic model is the hierarchical or nested logic model. And the great feature of this model is allows to handle a very important element, which is correlation among alternatives, by grouping those alternatives that are assumed to be correlated, for example, that appear to be more similar between themselves than others, in what we call nests or hierarchies. For example, assume that we have a case where we are trying to model a car versus bus and versus underground. Now, both these three alternatives are fairly different. However, both bus and underground share being public transport, share being a mode where you don't have complete control, where you have to wait, where you have to go together with other people that maybe you wouldn't like to go with them. Instead, in the car, you go alone at your own rate. So those two alternatives are considered to be more similar than car. So we could say that maybe they are in a nest, which we could call public transport. And if we do that, we can test afterwards, and I will show you how, whether the nest is okay or not. And that is very, very useful. And this was a radical invention in the early 70s. Now, in that model, in the figure, I'm showing a model where I have a number of alternatives, a lot of alternatives, but I have joined in nest several of them because I presume that they are correlated. Then I will be able to test if they are correlated or not, using the data that we have in hand. In the case of the nested logic model, the utility function takes another error component. We assume that the utility of choosing alternative I in nest J is given by the summation of the utility of belonging to the nest plus the utility of the alternative given that it is in the nest, Bi given J, plus an error for the nest, another error additive for the alternative. And in this particular case, when we do that, we get and a model which looks more or less like the one in the figure here, where we have now two scale parameters, one at the level of the alternatives inside the nest, lambda j, and one at the level of the superior nest, which we call beta. And then as you can see, beta is divided by lambda j in the end. And we cannot estimate both beta and lambda, but we can estimate the ratio beta over lambda j. And there is here, in this model, according to the definition originally proposed by Hugh Williams, that beta has to be less than or equal lambda j for all j if the model is actually correct in the form that we postulated it. But as I said before, only the ratios beta over lambda j can be estimated. There is a very good paper that explained all this by Juan Antonio Carrasco and myself back in 2002, because there was at that time a great discussion among many top researchers about some of the properties of these models. This family of logit models, the multinomial logit model and the hierarchical logit model, were for more than 30 years the workhorses of the field. Everybody was using them and they were really good. Now, recent extensions to the discrete choice theory allow individuals to have, for example, minimum perception thresholds, instead of assuming that everybody can perceive any difference in the values of the variables. We can choose in elimination by aspects fashion. For example, if we have too many alternatives, we can discard some of them immediately because they really are not actually very good for us. I will make some examples if somebody wants to ask later on. Or in satisficing behavior, for example, you can say that you choose an alternative after searching for some alternatives. You cannot look at them all until you find a one which is reasonable, and then you stop the search, because otherwise it can be very costly. Or if you don't select that alternative which was good, then maybe somebody else would choose it if you don't take it. So there are many ways of choosing when you have too many alternatives or when the choice is complex. And we have worked on this with Victor Cantillo, with Felipe Gonzalez, and have produced models which are quite interesting in this sense. We can also have something which is very, very important. In transport, for example, it is actually very true that you have habit. When you choose a mode, you choose that mode for a long time unless there is a very radical change. And that habit or inertia is very hard to model, and you have to propose special ways of modeling in that case. And we have done that again with Victor Cantillo and with Francisca Yañez and other students of mine. All these elements, whether you are actually modeling in this more general sense or not, are very important when you are considering using the models in policy design. Now I will mention briefly data sources. Revealed preference, state preference, and panel data. Revealed preference data, for those of you that maybe are not familiar with this field, they consist of actually observations about what is going on in reality. In our case, we would have to observe the choices made by a group of individuals, the choice sets that they have, and we need to measure the level of service attributes of each of the options that each individual considered. And this is actually a bit costly and sometimes is not very easy to do. Also, we need socioeconomic data pertaining the individuals that we are going to observe in a given sample. Stated preference data, on the other hand, is data about hypothetical situations. So we ask respondents several, not only one, hypothetical choice situations in scenarios which are generated following an experimental design. These data are particularly useful when we want to evaluate alternatives which do not exist at present, or when some of the attributes that we are particularly interested in cannot be measured or observed in practice. For example, reliability, safety, comfort, things like that. So this is the field, this is the area where stated preference is particularly important. Finally, panel data refers to observations, typically of a revealed preference nature, from individuals that are observed at several points in time. So we observe people before and after an intervention, for example. We can have, in this particular sense, long and short panel data. Long panel data is when we observe people at intervals which are long, say a month, a year. Short panel data is when observe individuals, say, in several days. And we can also have a long panel with short panel interventions in the middle as well. The former, the long panel data, are classically associated with longitudinal data rather than cross-sectional studies. And we have a very good paper with Elizabeth Takerki and Cynthia Cirillo on that, which you can check later on if you wish. Now, I will refer now a little bit about experimental design and some applications, because I think this is quite interesting for you to see the kind of things that we can do in this field. As I mentioned before, in state preference applications, respondents are given a set of hypothetical scenarios with 2 or more alternatives to choose from, and these alternatives are based on predefined attributes and levels of variation. And here I'm mentioning a paper by Cosad, Hencher, Luis Risi, and myself, where we studied how important it was to have the number of attributes, the number of alternatives, the number of levels of variations, and whether that was actually conflicting with the idea that people are able to choose rationally, because you can have too much burden on the respondent, and maybe the respondent would start answering in a different way to what the person would do if the burden wasn't so high. So that paper also is quite interesting. Now, individuals can typically choose between alternatives. They can rank alternatives from best to worst, or they can indicate how happy they are with a given alternatives using a semantic scale. For example, I am very happy with this alternative. I am reasonably happy with this alternative. I am okay with both of them. I cannot decide, and so on. So these 3 kinds of answers can be dealt with models, and they are quite useful. And if you want, you can go and see chapter 3 and chapter 8 of my book, and there is a lot of explanation about it. But before we can actually have the respondent and the hypothetical scenario, we need an experimental design. Up to the 1990s, experimental designs were always orthogonal designs borrowed from the traditional work in linear models. In linear models, the experimental design have been done for many, many years, and there are books about them. However, in the case of our highly nonlinear models, orthogonality is actually not a useful property as it is, for example, in linear regression. In the case of nonlinear models, orthogonality is not a useful property. What is much more useful is to have a design that allows you to have the lowest values for the variances of the errors. And that is the high priority, and what we now do is called efficient designs. These efficient designs are typically based on minimizing some measure, for example, the D error, associated with the covariance matrix of the estimated parameters. John Rose and Michael Blimer have done a lot of work about experimental design using efficient designs for many, many types of models. And I recommend very strongly to read the papers by them if you want to get into this area. What follows in the next couple of slides, I will show you some examples, particularly graphical examples of the way in which we use the web and special design pictures to represent a task that to respondents that would be otherwise very difficult to present to them with words. And in the later case, in the second example that I will show to you, we obtain very good results in spite of asking poor and less educated people to deal with a fairly sophisticated experiment. So the idea of using figures, images, is actually very good, because even people which have not a lot of education, we normally assume that they will understand less than a very highly educated people, still they are capable of answering these questions. So that is very, very useful. Now, the first one application I'm going to talk is evaluation of road fatalities in an urban context. And for this, we designed a route choice, a stated preference survey for people that use cars in different streets of my city, Santiago, in Chile. The instrument that we designed had 4 parts. The first one, we got information about the trip habits by the individuals. And they were also asked to mention a journey that was pretty usual. For example, the journey to work in the morning and the characteristics of this journey. And this data was used to customize the second part of the survey. And when we asked for the hypothetical scenarios, we used a real trip because we wanted the person to be really focused on something that he knew or she knew very well. Then there was a second part of the survey, which was the choice context and the stated preference exercise, which in the end were a series of binary route choices that I will show you later. Then we asked for information, and this is very useful, so you can take note about this. What was the opinion of the respondent about the quality of the stated preference experiment? As we are putting to them hypothetical scenarios, we really need to know whether they consider the scenarios or the choices realistic. Because if the choices are not considered realistic, then most probably the individual will not answer correctly, will not answer with their heart. And we need people to answer with their hearts. And also, we asked them about a road accident experience because we felt that maybe people who have had an accident or who had a relative who had had an accident would answer differently to a person that didn't. And there was a general attitude also towards risk, whether people were risk averse or risk prone. And finally, the survey always ends with socioeconomic data, because socioeconomic data, when you ask it, people are reluctant to give it. So you leave it at the end so that people don't get annoyed before in survey. Okay, so with that data, we have a context that was designed on the basis of this usual trip information provided by the respondent. And the data allow us to generate some items to which the respondents would have to pay special attention. And these are shown in blue in italics in the next slide. These were the journey purpose, the type of day, the arrival time, and the street predominantly used during the trip. These elements could vary in the design and were allowed to do so in what we hope they were realistic ranges. And to make sure that each individual considered the same street features in every choice situation, a picture of the street that was predominantly used during the journey was presented in the web page survey. So here you have what the web page survey looked like, more or less. And I won't read everything, but basically it mentioned that you have to travel to work on a regular working day, which the people have mentioned that before, at 7:45 a.m., because that was the time that he had mentioned before. You drive your car and you pay for all the travel costs involved. At the time you travel, the trip takes between 30 and 35 minutes. That was what the people have mentioned. And it has an average travel cost of $1. We calculated that assuming a certain fuel and car maintenance values for the kind of car the person had. And assume that you have to follow a route which by a street which is similar to the one shown in the figure. And there you can see a typical route in chaotic Santiago, which might not be so different perhaps from a Chinese city. And then you have to consider in the survey the following 3 characteristics: travel time, travel cost, and here was the key one: number of car accidents with fatalities per year. Now that information is usually not known by people, but we had calculated it and we had produced figures which were reasonable, and we presented it in a per year basis because they are very few. I mean, we may have 30 or 25. So if we want to have a variation, we need to have a year basis, because if we go by day, it wouldn't be a very small amount. And then in what follows, you will have 9 situations, and you have to select in each one which is the one you feel more comfortable with. And that was the way we did it, and it worked really well. And there is a paper with another of my students that I will mention later on. A key design feature here was to determine a clear way to present the chosen attributes during survey. And for this, we had carried, and I recommend this very strongly, focus groups before. Focus groups are a group of people, say 6 to 10 people that are joined together in a conversation, typically led by a sociologist or a psychologist, and where the researchers are hidden behind a certain screen, and all the thing is recorded, and we ask them about the circumstances of the kind of experience that we want to model. These are very, very useful to actually determine which are the best ways to present the experiments, etc. In this particular part of the survey, we concluded that a key element in conveying the meaning of the risk variable was to use the word fatality. We have to resort to the word fatality because it had been proved to be quite actually had an impact on the people and made it really concentrate on what we were trying to understand. Instead, if we have used, for example, the probability of having an accident, that didn't mean very much to anybody. And we have found that the number of car accidents with fatalities per year had worked very well in previous cases where we have done it in interurban travel. Okay, the second example I want to mention, and I have to hurry up, I think, a little bit, is trying to understand how people value safety when they have to walk through a neighborhood which might not be totally safe. And we were studying in this case then pedestrian perception of safety from crime. And we postulated a context of walking in an area during daytime conditions, because in the focus groups, we learned that at night, things are actually much more worse, and only one attribute, street lighting, is so important that kind of hidden all the rest of the attributes. So we decided to study the thing at daylight. According to the theory of perception of safety from crime, there are two kind of macro or composite attributes which are very important. One is called natural vigilance. And natural vigilance is kind of, if you're walking in a street and you have houses and there are people inside, and maybe they're looking at the windows, or maybe there is a shop, or maybe there is a public transport passing by, or maybe there are other people in the street, then you feel safer than if the street is totally alone, lonely, and with no houses, and it's kind of, you fear that maybe somebody will appear and rob you. Maybe in China, people are not so bad, but in my country, it's quite possible that you get robbed in a street like that. And the other one variable, which is very important, is visual control. Visual control is how do you as an individual feel about the control you have that the situation is under you, that you can manage it. For example, if you're in a street which has a lot of trees or has kind of alleys and things, you fear that maybe there will be somebody hidden there and maybe can attack you. Instead, if the street doesn't have anything and doesn't have alleys and is kind of looks nice, you feel safer and you walk with more confidence. Now, we tried to relate these two macro composite variables to physical attributes of the streets that we were studying. For example, whether there are windows whether there were fences, whether the fences were opaque or see-through, whether there were people, whether there were kiosks, etc. And I will show you what I mean in a minute. Now, one key time that you want to work out a willingness to pay is to have a payment mechanism. Now, in the case of the previous example, there was the cost of driving the car. And if you are in an interurban case, you may have to pay a toll for using a highway. Those payment mechanisms are natural and very easy. In the case of walking in a street, what is the payment mechanism? Now, we studied this for a long time and did the focus group and did the Delphi survey and asked experts and did the literature. And eventually, we came up with a very useful concept. We invented something called additional mortgage. And the additional mortgage would be what people would have to pay to ensure that the house that they inhabited was located in the area that was perceived as the safest. So if you had to choose between two areas, two streets, and you say street B is safer, then I would ask him again, and I will show you, would you still choose that street if the payment to live in that area is higher than in the other one? This was actually quite well received and understood and worked very well, and we were able to define eventually willingness to pay here. So use of images was very crucial in this case, because you cannot have the idea of natural vigilance and visual control without having images designed on the basics of these physical attributes. So for example, what we did here is that we went to the area that we were studying, the poor neighborhoods that we were looking at, and we took pictures of them. Now, we didn't use the pictures themselves because a picture has a problem which is very difficult to control. And it is that, for example, if in the picture, say, the weather is much nicer in one picture than in another picture, people would tend to choose the nicer weather picture rather than the other one, forgetting about some of the things that we are considering. Also, there may be other issues that you cannot eliminate so easily from a picture. And this is very important. This is very important. So instead of using the pictures themselves, we constructed images of them, combining by layers in the form that is kind of shown in the picture to the right there. Okay. After doing that, we built the scenarios. And for example, the thing would go like as follows. Imagine that you're walking through these two streets. Where would you feel safer? And as you can see, the street to the right looks a little bit more badly maintained. The street is worse maintained. The garden is kind of worse maintained. However, you have a shop, you have a shared taxi passing by, and you have the same amount of people, and the street looks kind of not so different. On the other one, the left-hand side looks much better in the sense of maintenance, and you would feel safer in the sense that maybe the people that live there are less criminals, if you want. But on the other hand, you don't have the other. So you would have to say where you would feel safer to walk in here. And say you say A looks safer. Then I would ask you, now considering the mortgage payment and your feeling of security, where would you prefer to live? In the A case, where you have to pay a higher mortgage, $34 per month, or in the B, where you have to pay only $26. And this worked very well. Some people would still maintain that A was their choice. Some of the people would not, because they were not so different, so they preferred to go to the B. And there were 9 of these again with different. Some of them didn't have people. Some of them didn't have shared taxis. Some of them didn't have the kiosk, etc. So it was an experimental design. Now, we have applied this methodology to all these cases here. We have designed new pricing strategies for the underground, estimating the demand for network cycleways, willingness to pay for reductions in environmental pollution, noise and accidents, for social housing attributes, for air travel, bus driver preference in work shift structures, up to, if you want, sustainable mobility and natural reserves, wine preference when price is a cue for quality, and we did that with a Chinese university too, etc. So you can see here, and I will present afterwards a list of reference. We can apply these kind of methods to really anything that has a choice involved. So that is very important. Now, I want to go very quickly now, because I have spent a lot of my time, to show you the two more sophisticated models that we are now having as state of practice. One is mixed logic, and mixed logic has two forms of being formulated. One is the error components form, where you have the same as we had before. U is a utility deterministic, which would be theta j times x, and an error epsilon, but you add another error term. And this error term has, again, zero mean, a certain variance which is unknown, and multiplies this random vector by unknown attributes to you, to the modeler, which we call y, jqt. And this allows, if you do it correctly, to treat almost anything you want. error structure with correlation, cross-correlation, heteroscedasticity, you name it. This is really wonderful way of dealing with the problems that we were dealing before. For example, here, this is a way to represent an heteroscedastic logic model, multinomial. So you have your basic utility is theta times x plus epsilon, and you add simply a constant sigma I times this error, which distributes normal 0, 1. If you work out the covariance matrix for this model, and I can leave you this as a task to do later, assignment for you to do, you would come out to this covariance matrix. And the covariance matrix, as you can see, is instead of being the typical covariance matrix of an independent independent identical model, where all the part in the diagonal is equal. Here now we have the diagonal varies because it does have sigma 1 square, sigma 2 square, and sigma 3 square, which are different, and the rest is the same. In a multinomial logic model, sigma 1, sigma 2, and sigma 3 would be 0, so you would have an independent and identically distributed model. So that is very, very useful. There is also a more classical structure of the mixed logic model, which is called the random component structure, where instead of having the previous one, you have that you allow the parameter theta to be random. So you don't need an extra error component, but you have on top of your epsilon, which is the typical extreme value type 1 error, you have that the thetas are actually random, and they vary with density function f theta, which I will mention more in detail now. Now, in this case, the choice probabilities do not have a closed form. They are actually an integral of a standard logic probabilities over a density of parameters. So they are very complex multivariate integral. In this case, L of theta is the multinomial logic probability evaluated at a set of parameters theta, and the density function f of theta is known as the mixing distribution. This mixing distribution is very, very important because if, for example, it is degenerate at fixed parameters, that means if the value of the function equals theta, each theta equals b and 0 for theta different to b, then this is exactly the simple multinomial logic model. So the discrete, when the function is discrete and with fixed values, we have the mixed logic model collapses to the normal multinomial logic model. In the case of the distribution being discrete, but the parameter theta take values b1 to bm with probabilities sm, such that theta equals bm, then in this case, the mixed logic model becomes the latent class model. And the latent class model has a lot of applications in psychology, marketing, and lately also in transportation research. And this is very useful when there are distinct segments in the population, each with which their own choice behavior. And you can check the book by Train here to go in more depth in this particular example. And however, in most applications, the function is actually continuous with mean v and covariance matrix epsilon. And these parameters, which we call population parameters, are the parameters that normally modelers estimate, just the mean and the covariance matrix. However, and you can postulate here many types of mixing distributions. So there is a potential source of misspecification when you do not do this right. I tend to use the normal distribution because it has a lot of very good properties, and we can talk about this later if we have time. The mixed logic model has another set of parameters, which are the values of theta for each individual. And these have density f of theta conditional on the population parameters beta and sigma. And this can also be estimated using Bayesian methods. And I recommend to you strongly to look at this paper by Silano and myself in 2005. It's very good for showing very, very easily what I mean here by estimating the parameters using Bayesian methods. The presence of this vector x in the covariance matrix helps to ease a very complex problem of identification which are much more difficult in the mixed logit model. Identification is much more difficult in the multinomial logit, in the mixed logit model than in the multinomial logit model. Remember that in the multinomial logit model, identification was only related with the problem of having escape parameters, which we cannot identify, and also and has to be normalized to 1 typically, and also that one constant needs to be 0 because there is a reference alternative. In the case of the mixed logit model, the conditions for identifiability are much more stringent and complex. The second state of practice model is the hybrid choice model. And this model has the beauty of incorporating latent variables. And latent variables are factors or variables that influence behavior, but their influence cannot be quantified very easily in practice. For example, we may have variables such as comfort, reliability, and safety, or even more important, perhaps we can have individual traits such as risk aversion or being green, concern for the environment. And those two things, they cannot be measured easily. So we have to record to latent variables to allow to have a measure of them. And this is because either they're intangible, they don't have a measurement scale, or because they are really subjective. So the different individuals may perceive them very, very differently. Now, the identification of these latent variables requires us supplementing a standard survey with questions which are designed to capture the perceptions regarding certain aspects that otherwise could not be measured. So we need to postulate perception indicators, and I will give an example later. Here, for example, I have 3 sets of statements which are associated with indicators that have to do with habit, insecurity, and being green. For example, the statements would be, I do without having to consciously remember. I start doing before I realize I'm doing it. I do without thinking. Now, all these statements, you ask the individuals to rate in a scale, a Likert scale, which says, I am completely in agreement, I am more or less in agreement, I am neutral, I disagree more or less, I disagree complete. So it's a 1 to 5 Likert scale, and you have all these indicators, which we have labeled here, without remember, awareness, without thinking, automatic, or in the case of insecurity, broken bike, robbery, accident, or in the case of being green, mode shift, car pollution, air quality. Now, these things are very important because sometimes, for example, in the case of habit, the phrases look very, very close. However, incredibly, and this is a psychological thing, psychologists are great after all, people actually react differently to some of these things when you ask them to rate them in a Likert scale. For example, here, for the 5-point Likert scale I mentioned before, the summary of habit indicators was shown here that, for example, without remember, 28% of the people put a 5, awareness only 18, without thinking 21, and automatic 45. So there is a difference, although to me at least, they look very close. And in the case of the other perception indicators, also there were variations in the way they were responded in a sample that we used in a model to study habit, the influence of habit and these other latent variables in using bikes. Very interesting study. The hybrid choice model has then explanatory variables, indicators, and they go into eventually into the utility, and the utility eventually determines the choice. However, including the indicators directly in the utility function is not a good idea, although it has been used in the past sometimes, because the indicators are not causal, and they are highly dependent on the phrasing of the survey questions. So, and also they are not available for forecasting. So what do you do with them when you put them directly in the utility function? Now, to treat properly the indicators and the latent variables, you need previously a mimic model, multiple indicator, multiple cause, which is a kind of structural equations model, where the latent variables are explained by characteristics from the users through structural equations, like the one I'm showing there, where the latent variable is explained by the x variables, and there is an error v. At the same time, the latent variables explain the indicators through what we call measurement equations. So here the indicators Y are explained by the latent variables, and there is another error. And these errors are all of them with mean zero and a standard deviation that has to be estimated. And there are also conditions that have to be met in terms of identifiability, etc. As the latent variables are unknown, both these equations have to be considered jointly in the parameter estimation process. Current practice, this is another thing. Because the measurement equations are typically ordinal, because they are based on a discrete Likert scale, instead of having a linear equation, like a linear regression to estimate them, we use normally now an ordinal logic model. And an ordinal logic model would be a model which has the following form. You postulate that the parameters to be estimated depend also on some thresholds, which are defined by the Likert scale. So the indicator 1 would be 1 if the variable, latent variable yi, is less than the threshold, would be 2 if the variable is between the thresholds 1 and 2, and so on. And this way of estimating the model is much more powerful, and it has been shown to be better in many applied cases. Now, what happens then at the end with this model? You have your latent variable model, which uses the explanatory variables, the latent variables, and the indicators, and that it produces the latent variables values, which are put in the utility function together with explanatory variables, together with the error epsilon, and that determines the choice. So you have a latent variable model on the right top and a choice model on the bottom. And these models can be estimated sequentially, and this was the only way that we could do this in the beginning of the story, which was in the 2000s. But it has been shown to be not capable of producing unbiased estimators. And so sometimes we underestimate also the standard deviations. And there is a very good paper by Juan de Dios Ortúzar, a student of mine that now works in Germany. And now and this can be solved, but it's very, very tricky. So now we estimate them jointly. And to estimate them jointly, we need to replicate the individual choices based on the representative utility proposed by the modeler. But we have a conditional probability, which can be expressed in terms of the variables and parameters of the discrete choice model, like that. And because the LB are not observed, it is necessary to integrate over their whole variation range, conditioning them by their explanatory variables. So we need to add the density function of the latent variables. So we would have that the probability that we have to estimate is an integral of these previous probabilities times this density function. However, we still need to estimate the model with the information provided by the perception indicators, as otherwise the model would be not identifiable. And these are not explanatory variables. They are endogenous to the latent variables. So at the end of the day, we need to also incorporate the probability density function of the indicators. So the final probability is a really, really complex integral incorporating all these things. And that works, and we can estimate it with packages that are available now. For example, there's a very nice package called Apollo, produced by Stefan Hess and David Palma in Leeds Choice Modeling Center. And but the problem is that they take really a long time to run. So it's very, very difficult to test things with them. Now, the process, as I tried to mention, is extremely involved. In the case of the bike example I was showing you before, with 3 latent variables, habit, insecurity, and green, modeled using an ordinal logic for that part of the model, the process takes 6 hours to converge in a very powerful computer. So we are talking here of long processes if you want to have good estimates. Okay, finally, and I'm only 2 minutes away, I would like to talk about modeling with mixed RP-SP data, because we have some disadvantages of using state preference data, because we're never sure whether the information is actually too reliable. So the proposition is to combine SP data with revealed preference data, taking advantage of the mutual strengths of both methods. The main difference between both types of data is that the nature of the associated error. In the case of RP, where are the errors? The errors are when you measure the independent variables. measuring independent variables in the field is actually complex and difficult. In the case of SP, the error is of a more tricky nature because the error is in the dependent variable. You are never certain that the people will answer truthfully to the hypothetical choice scenarios. So the mixed data paradigm, we aim to build a model to make appropriate forecast. So the RP data may have deficiencies, identification, low variability, and the SP data is very good for attribute valuation, but suspect in predict terms. So combining the model is the best of both worlds, if it works, and there are methods to do that. So what we did for a long time was using something called the nested logic trick. I will not talk about it, but the problem was that there is a key issue here. The speed choices made by one individual are not independent. And in the previous way, we have to consider them independent. Also, the speed choices, if they are based on an RP previous trip, for example, we call that pivoting, they are not independent of the RP trip either. So we have to incorporate into the modeling the pseudo-panel nature of the data because we have several observations for individual, and also this correlation with the RP. And with the mixed logic problem, with a mixed logic model, this can work very, very easily. And I show you how to do this in chapter 8 of my book, so I will refer to you there. So in summary, discrete choice models allow us to estimate the parameters, weights, or marginal utilities, or attributes in context involving choice among several alternatives. Alternatives can be correlated. The error terms can have different variances. The parameters can vary randomly in the population. However, interpretation of results in those cases is more involved, and there may be difficulties with properly identifying different effects. There is something called confounding, which when you allow for random coefficients, you are in a little bit of a problem. So I recommend trying to do systematic taste variations with a mixed logic model of an error component form rather than random coefficients model. We can also handle choice contexts where there is habit or inertia, treat the possibility of having thresholds of perception for some attributes. We can even consider different choice mechanisms such as elimination by aspects on satisfaction. And these mechanisms can be particularly important when dealing with choice contexts which have too many alternatives. For example, if you're choosing where to live, there might be 100,000 alternatives. There is no way you're going to explore them all, so you have to treat them in different ways. Conclusions, I have provided a glimpse of contemporary discrete choice modeling with reveal and stated preference data to illustrate the potential of these techniques in modeling customer behavior for market analysis and help designing appropriate public policies. Experience in doing this has shown in several applications, it is not always straightforward. It is actually difficult. You have to be serious. You have to be really concerned about the design, etc., etc. However, some of the advantages of using this discrete choice approach are such important that we can obtain valuable information about the relative weights of the attributes of any kind, level of service to latent variables, and the willingness to pay for improvements in any of these attributes. And this is such an important advantage that merits the effort necessary to make this possible. So here is finally a list of reference, and I can send Sunny the presentation so that you can look at this reference in more detail of my experience with these things. And I hope you enjoyed the talk. Thank you very much.
Okay, Professor Juan de Dios, thank you for your presentation. And it's very impressive, yes. So finally, I want to say thank you, and for the audience, thank you for coming. And we want to thank our host, Alex. Actually, Alex currently is in Hong Kong. He's our colleague, and because of the COVID, and he has to stay in Hong Kong. Actually, we cannot launch the Zoom meeting in mainland China, but he can. Yes.
Ah, well, excellent.
Yeah, yes. Thank you, Alex. So for the audience,
nice to meet you.
Alex, you may simply introduce yourself.
Hello, I'm Alex. Yeah, I'm the assistant professor in JNU working with Sunny as well. Yeah, I am doing research in MCD, in the multi-criteria decision-making method and the human behavior with technology, yeah, such as the virtual reality. And I think your presentation is very impressive, especially for the second experiment. I think you can consider using virtual reality as well, like exploring the street or the houses. Yeah.
Yeah.
Yeah. Okay.
It was
So
very interesting.
thank you, Professor.
Yeah, thank you.
Juan de Dios. Yes. In your presentation, you first introduced the basic discrete choice model, and then you moved to 3 types of data sources. Then we introduced experiment design and give us some applications. And then you just introduce some advanced models like a mixed logit model and some hybrid choice model like mimic model. So that's very interesting. And so for the audience, so do you have any questions? Yes.
I am very sorry that I have to rush at the end because I got carried away with explaining at the beginning and then I forgot I have too many things to show you. Sorry. Yeah?
It's okay. It's okay. Yes. Yongli Tang, Professor.
Hi. So good morning. Good morning, Professor De
Yes,
Dios.
good morning. Yes.
So I'm Yongli Tang from School of Management in Jinan University. So I'm in a completely different in Guangzhou, in a completely different research area. So I'm doing some research on university industry, collaboration, and so we come across some issues, some research questions about the matching and selection. So between the the firm and the university, from both sides. So I have a. I mean, the discrete model you just introduced is very interesting. We have been considering to use experimental design to investigate. So, for example, the trade-off, the company or the university side, their trade-off of the attributes of the other side partner. For example, their capability, proximity, experience or previous relationships or something like that. But there is one thing I would like to know your opinion about the experimental design. So because there are many attributes and there are many different levels, so the combination is like explosive, the number, too many combinations sometimes. I mean the choice set. So do you have any suggestion on how, first, like how many options can we give to the, for example, to the respondent in the survey? For example, if we have 30 choices, so how can we deal with that in a survey?
Right. Thank you very much, Professor Tang. This is a very interesting question, and I would really be glad to if you send me an email to my I don't know whether you have my email, JOS. I will write it down.
Yeah. I have it in your slide, I think.
Okay. Yes, there in slide it was. Well, if you write me an email with more details, I can probably help you more. But let me say a couple of things. First of all, this experimental design is a really key element in all this work. Mm-hmm. So I would suggest that after you have really understood the problem well, hopefully talking to the client, with the customers, with the doing focus groups, etc., you come up with a list of attributes and etc., and you realize that you have too many. Now, it is not advisable to use them all, really, at least in a one experiment. Mm-hmm. We have written at least 2 papers which are very interesting. The one that by Cosad et al. That I told you about, look at the problem of having too many attributes, too many alternatives, too many choice situations, etc. And we came out with some recommendations there. But then afterwards, my friend John Rose took this data that we have collected in Chile, and he collected some similar information in Australia and similar information in Taiwan, and did a comparison across cultures and across nations of the capability of people in these different environments to treat too many alternatives, too many attributes, etc. And it was very interesting because it turned out that the people in Taiwan and the people in Australia were in fact better at dealing with more alternatives, etc. than the Chileans. The Chileans are more lazy. So we are not very happy with too many alternatives, but the people in Taiwan, for example, were. However, it was never 30. It was, say, 5, 6. Now, if you have 30, there are several ways of dealing with this. If there are attributes, in the design, with the efficient designs, instead of orthogonal designs, maybe you are using an orthogonal design. So
orthogonal design.
Yeah, orthogonal designs are not very good because they yield to too many options. Efficient designs are much more efficient in the sense that you don't need too many alternatives to do to collect the data that you really need. On the other hand, when we have, for example, more than, say, 5 alternatives, instead of presenting 5 alternatives, we would go for an experiment which presents 2 and 3, and then join them together in a certain way. That can be done too. So people are happier to answer 2 experiments in a row than to answer a single experiment with more alternatives. And there is a lot of knowledge about these kind of things that might be useful in your own case.
Thank you very much. So efficient design is new to me. So I have thought that you have listed a reference on efficient design. So I will look into your paper about it.
Yes.
Thanks.
John Rose and Michiel Blimer, those are the 2 guys.
Okay, thanks. Thanks. Thank you very much.
Thank you.
Professor Juan de Dios, actually, I have similar question, yes. So in your paper, you may propose how to evaluate whether the experiment is efficient or not. So you may provide some common ways to evaluate its design. Is that true?
Well, actually, yes. It's not exactly like that. There is now even a software called Engine. Engine is very, very nice because you can do it on your own self, but that was done originally by John Rose, and he eventually created software, so it's much easier now to have that software. What you do is you start looking at your design. It's an iterative process until you find out the design that produces the least value of the diagonal in your variance convention matrix of the estimates. Now, for doing that, you need to have prior values of the estimates, and that is a little trick of the efficient design. You need prior values. So what happens when you don't have prior values? Well, when you don't have prior values, the recommendation, fortunately, the recommendation is easy. You actually do an orthogonal design, which is not very good, and you go and collect a pilot sample. With the pilot sample, you estimate a model, and that model gives you prior values of the parameters. And with the prior values, you then do a much better efficient design. But it's an iterative process. It's not simple.
Okay, yeah. So the software is commercial or not? It's commercial, the software?
Engine? Yes.
We have to develop some component by ourselves or not?
No, you look. If you are an academic institution and you want to do this for more than anything for research and teaching, you can get Engine for free.
Okay.
So, write to John Rose at the Technical University of Sydney, I think it is now. Look at him, John M. Rose, Professor John M. Rose. I can't remember where he is now. He used to be in Sydney, but now maybe he's in somewhere else. And he will send you the program, or the value is not very high either if you want to use it for other purposes.
Okay.
Not very
So,
expensive.
actually, in your presentation, you describe the imaging design in SP game. That's very interesting. Yes, you give us two images, and one
Yes.
have to pay 34, and another pay 26, and in such a way you can evaluate the willing to pay. That's very interesting. And so my question is that can we use the photo token by mobile phone or just camera? Because in your slides you use the image generated by software.
Yes, the thing is that what I try to explain is that if you use the photographs, the real photographs.
Yeah, can we use it?
The real photographs have the problem, unless you actually work with Photoshop or something like that, they have the problem of having extra elements in it that may catch the attention of the individual to something that you don't want him to look at. Because
I understand.
Like him to concentrate on the things that you really need. So maybe now with Photoshop you can do it, but it's very tricky because real pictures have too many things that may vary, that may distract your attention from the things that you really want the people to concentrate.
Okay. Yes. Thank you.
I have worked a lot with people from the School of Design and the School of Architecture, and they are really good at producing these images from pictures.
Okay, understand. Yes. So finally, can you show us the slides for free?
Yes, I will send you the.
An email. Yes, send me the email. Yes. Okay.
I will send you by email my presentation so that you can have it in there in yours.
Okay. Yes. So I just told everyone my email, and if they have any question, can send me email.
Okay. Right, because I will have to leave in about 2 minutes because I have another meeting.
Okay. So see you. Maybe see you. Yeah.
Okay. Thank you very much. It was a great experience, and I hope, as I said before, that we can see each other in real person sometime.
Yeah. Keep in touch. Yes.
I will.
Have a nice day.
Bye-bye. Thank you very much.
Okay. Bye-bye. Thank you. Alex, bye-bye.
Bye-bye. So see you everyone, and thank you.